this is a famous result, and that's the reason I thought I'd talk about this in terms of it's a famous approximation. When the asset is at the money forward, i.e. when the strike price is the following, then we say that the option is at the money forward. In other words, E is equal to this. So there's a class of options called at the money forward options, and the reason why is because essentially the forward price, obviously adjusted by the D term there, the minus D, right? So it's also tends to be a popular interview question. In other words, obtaining this approximation when you are close to expiry. Close to expiry meaning that big T minus little t is very, very small. As t tends to big T, you can obtain this approximation from this rather messy looking expression up there. So let's start off by looking at this. Here's the price of the option. And what I'm going to do is I'm going to write down big T minus little t as tau. So we're saying that this is what the price of the option is, where tau is big T minus little t. For an at the money forward option, we have that E is equal to this. So we substitute this into the expression above. We get S e to the minus d tau n d1 minus S e to the r minus d tau minus r tau n of d2. So it becomes S e to the minus d tau n of d1 minus n of d2. This is what the price of an at the money forward option would look like. However, we want to try and obtain that approximation which is given at the bottom of that slide. Now what we need to do is we need to work on the d1 and the d2. What happens to d1 and d2 when E is equal to S e to the r minus d tau? So here's d1, d2. So there's d1, d2 is equal to log S over E, and E is S e to the r minus d tau. That's d1 and d2, right? So that's what we're going to write down. So plus r minus d plus minus a half sigma squared times tau over sigma times tau, square rooted. If you don't mind, what I want to do is I want to, on the same slide, use red to do some cancellations. So this S cancels with that S. If I bring the exponential upstairs, it becomes e to the minus r minus d, right? And the exponential and the log cancel out. Agreed? So if I can do that on here, so that log there will cancel with this, and that comes upstairs, and what we end up with is minus r minus d tau. Agreed? Right, can you repeat? You said at the money forward, is that E or little t? You said at the money forward, is that, where did I say that? Oh, sorry, are you talking about that E here? Michael, if you're talking about that, that's a capital E. Sorry, sometimes I always say that my diagrams do come with a health warning. I think my writing is going that way as well. That's E for expiry. So sorry about this. It took me a while to figure out what Michael was asking, and it's a perfectly valid question because it does look like a little E, I think. So now, can we do the other step to do is we get rid of that term with that term. Agreed? All right. So I know I'm cancelling all this. It just means saving space and getting you to write down less. So this is going to cancel with this, right? That squared goes with that, and then if I cancel this, this becomes the square root. So what we're left with is a very nice thing, which is a half sigma root tau. So D1 is plus a half sigma root tau, D2 is minus a half sigma root tau. And that's what these become. So I'll wait for you to, I actually might be able to squeeze some more on this page, so let's try and do that. Now, n of D1 minus n of D2, what does that become? Now, before we can do that, what we need is, we're talking about this approximation is only available close to expiry. Now, how many of you when you went to universities, you used formula books for, say, engineering or science? Anyone here? Right, so just the one person here. So typically, for engineering type courses or, say, physics, historically in the UK, engineering undergraduates have had access to very large formula booklets, about that big. And they have all sorts of well-known formulas in there. One of the things that's been particularly useful is approximations for the cumulative distribution function. In other words, that curve, many people have come up with different approximations to that. Now, there is one which is due to a pair of mathematicians called Kendall and Stewart. And what they proposed was the following. They came up with the following. So this is due to Kendall and Stewart. They said that n of x is a half plus 1 over root 2 pi times x minus, now I'm not sure about the next term, it's definitely order x cubed, but then you've got an order x to the 5 term after that. And when x is very small, obviously it's the leading order term that's going to dominate. So n of x then becomes approximately a half plus x over root 2 pi. Now, what can we say about n of x plus n of minus x? Under this approximation, well, the halves are going to cancel out, and what we're going to end up with is 2 lots of x over root 2 pi. Now, when x is equal to a half times this, what do we end up with? N of a half sigma, because this is what D1 and D2 are, aren't they? We end up with this minus that. So it's 2 lots of that. So it becomes sigma root tau. Agreed? Now let's go back. I'm just going to go back for 1 second. We're going to put that in here. Okay? We need the root 2 pi. Have I got the root 2 pi in there or not? Yeah, so I also need that. So it's 2 lots of that over root 2 pi. Agreed? What's 1 over root 2 pi approximately? Yeah. I know. I was hoping somebody might have a calculator just to verify. But it's about 0.398 something, right? So this is approximately 0.4 sigma root tau. Let's put everything together now. So we've got an S. Finally, we can say we've got, remember it was S e to the minus d times tau. So times all of this stuff. So 0.4 sigma S e to the minus d times t minus t times the square root of this. That's what it becomes. Now, is that what's written on the slide? Yes? Sorry, is something missing?
It's a minus in the third equation. N of x minus.
Yes, thank you. Very good. Right, so can you just make a note? Our friend has corrected me. That's a minus there. All right, so now you know how to obtain that approximation. So having done the call, should we look at the put? With the put on the same underlying and exercise features of the contract, you're not going to go back and solve that awful equation again or work on that integral. What you will simply use is use the put call parity. You will substitute C into the put call parity, rearrange for P, and that's what you get for the put. Right, so the value of a put option can be found in the same way as above. Not a good idea if you've already got the call, or using that parity. And what Paul's done is he's done the two-dimensional plot as well as the 3D plot. Okay. And also written down what the solution is in the presence of a continuous and constant dividend yield. So what you can do is, why don't you try this as an exercise? You know the maths we just did a moment ago to obtain this? Do the same thing but using this formula. Okay. Formula for a binary call. Now we talked about, I think we talked about binaries in the binomial model. Remember? Whether we call these binaries or digitals, we mean exactly the same thing. So what we have here is the corresponding Black-Scholes prices for binary options, okay, which we went through earlier on. And then we also talked about the put call parity, didn't we, earlier on, that you get the discounted $1 or £1. So once you've priced these options, if you happen to be in the business of managing risk, then one of the things you want to work out or be interested in or concerned with is the sensitivity. If there's a small change in the underlying, how does it affect the price of the option? Right? And those kind of sensitivities can be obtained using the Greeks. And the only reason they're called the Greeks is because there's a set of Greek letters to denote each one. The most frequently used one, and the one that you've seen quite extensively so far, is delta. And delta is probably the most commonly used Greek by all practitioners, because in terms of its fundamental importance, it's precisely the amount or quantity that we need to know in order to delta hedge, i.e. how to eliminate the risk. So delta, think of delta as being a bit like the velocity. You want to know how your displacement is affecting the change in the velocity. So the change in displacement with respect to time, it's a bit like delta. One way of appreciating this is to go back to our Taylor series expansion and say, well, what happens? So here's a Taylor series expansion. Here's V as a function of S plus delta S, comma T. So we can write this down as V of ST in this calculation, I'm not going to allow the t to change because we're just focusing on s. Plus dv by ds, delta s, plus a half, so 1 over 2 factorial, d squared v by ds squared, delta s squared, and so on. Dot, dot, dot. Now let's suppose that delta s is small. Right? The change in the underlying value of the stock is small. That means that everything else is going to be negligible compared to that. So that will give us an approximation. So if you were to rearrange this, you take the v on the other side and divide through by delta s, you've got dv by ds, which is the first order partial derivative of v with respect to s. And that's the delta. So we can write down that this is delta. It's essentially our linear exposure. Okay, so that's delta. What you can do for practice, and I think there is a problem in the sheet, exercise sheet, is you know what the Black-Scholes formulas are for these plain vanillas and also the binaries. Try calculating some of these. Now let me just start you off on the very first one, right? The call option. Because there is a trick involved here, that is the chain rule. We know that C is equal to S n of d1 minus this, n of d2. Is it all right if we just focus on the very first one? So we'll just look at calculating this. This is easier, and if you understand this, you appreciate this, then that's straightforward. So let's just focus on this. So delta is equal to dc by ds is equal to, so clearly we need to use a combination of the product rule and the chain rule. So if we say, keep an eye on this, dn by dx is simply 1 over root 2 pi e to the minus a half x squared. And if you want to know where that came from, Leibniz rule. This is differentiation under the integral sign. That's where you get that from. In calculus, Leibniz was responsible for two main results. One was for the nth derivative of a product, and the other one was for differentiating with respect under the integral sign. Because remember, n is an integral, isn't it? So if you differentiate that with respect to the upper limit, then Leibniz rule gives us that result. Now, S times d by ds of n of d1, right? How are we going to calculate this? We're going to use a chain rule. Why? Because this is a function of a function. N is a function of d1, d1 is a function of s. Agreed? So you would break this down as follows. So first of all, you'd say dn by d1, and then you'd say d1 by ds. So that's the only trick you really need. And if you think about, well, let me ask you a question. Here's d1. What do you get if you differentiate this with d1 with respect to s?
T over D over.
Well, if you ever get stuck on something like log s over e, just write this down as log s minus log e. Log e will vanish, so you're going to get a 1 over s over there together with this term here. Everything else after that is going to vanish. It doesn't depend on s. So it's not that difficult once you start doing this. Okay? And the very first one here, that you can obtain from Leibniz rule, this is going to be 1 over root 2 pi e to the minus a half d1 squared. Right? So something to get you started. Okay? That's something for you to try. Right. Now, let's go back here. You want to see how fast your delta is changing. How much money are you losing to transaction costs, for example? Because if you are having to buy and sell in order to keep your portfolio delta neutral or eliminate the risk, that's going to be picked up by gamma. But more importantly, gamma tells us the sensitivity of your delta with respect to the underlying. So this evening, this is the only example of a second order Greek that we're doing. Okay, which is, so gamma is equal to d by d delta of ds over ds. So if we go back, we can now write this term here, we can write down as gamma. Which means that if the change in the underlying isn't actually that small, and it's actually quite large, it means you have to be very careful about the contribution coming in from here, because you can't ignore this now. So you'll see a lot more of this, not only in Espen's lecture, but also when you do the volatility stuff, the advanced volatility, and you look at volatility arbitrage. Right, so that's coming up. Right, so again, some common gammas. So if you manage to write down the formula or derive delta for one of them, differentiate it one more time to get the corresponding gamma. Right? Just try one. Just pick one product and calculate all the Greeks for that. It's free practice essentially, in terms of you'll get to do a lot more differentiation on some of these messy formulas. Theta is the rate of change with respect to a change in 1 day. But normally what happens is that, again, t is not a very good measure. So more commonly what happens is that we tend to write this down in this form. When that decreases by 1 day. In other words, the sensitivity of V with respect to a change when this decreases by 1 day. So this is the one Greek that tends to have a negative value. For that reason, it's also sometimes called the theta bleed. And that's theta. You do get some people memorizing some of the simple Greeks until you see this. And maybe it's not such a good idea trying to. Again, if you've chosen one particular option price, then maybe try this as well. Just the one. There's no harm. Okay. Vega, also known as zeta and kappa. There is no Greek letter vega, is there? No. So this is sometimes regarded as a bit of an odd Greek in that respect, because there is. So, and that's the reason why it says here sometimes, because zeta and kappa do exist in the Greek alphabet. So sometimes what people will do is they'll denote this with a kappa or a zeta. Right? So when there's a change in the volatility, a 1% change. However, we know that when there is a change in the volatility, it might be in terms of the basis points. So this is Vega. and then we have rho, sensitivity of the option value to the interest rate, again when there's a change in 1%. Does anyone know what rho and vega are sometimes called informally? Yes, that's correct. Yeah, and it's really because of what I just asked. But more importantly, actually, there is another reason. What did we say at the beginning in our assumptions about sigma and they're constant, and now you're supposed to be considering these as variables, and that's the reason for that particular name given to them, because it just doesn't make sense, right? So that's vega and rho. We can now also write down the Black-Scholes equation in terms of the Greeks. So the Black-Scholes equation we can write down as dv by dt plus a half sigma squared s squared times d squared v by ds squared plus rs dv by ds minus rv, which we take to the other side. So here's the Black-Scholes equation written down in terms of the Greeks. Okay, happy with that? But just going back to what we were saying about the fact that these can sometimes be thought of as bastard Greeks. If we just go back to vega for a second. Well, one thing you can also do is you can write down the Black-Scholes equation in terms of the Greek, in terms of vega, for example. And the way we can do that, so what we would do is, what is the name for vega and rho? Do you mean in terms of, I'm being asked what is the name for vega and rho? Do you mean in terms of the Greeks? Because in terms of the Greeks, the other one, I think the other one's written down, isn't it? Is rho, yeah, there we go. What is the name? Okay. This is something that's done quite frequently. Rather than solve the Black-Scholes equation and then try and get sensitivities from there, what we do is the following. Take the Black-Scholes equation. So here's the Black-Scholes equation. dv by dt plus a half sigma squared s squared d squared v by ds squared plus rs dv by ds minus rv is equal to 0. I'm going to differentiate this like this. Okay, so, and the other thing we're going to assume also is that we can change the order of the differentiation. In other words, I can write down, we've got d by d sigma of dv by dt. I'm going to swap those around. Okay, so I'm going to then write this as d by dt of dv by d sigma, like that. Right, that's how I'm changing it around. Plus, we've got d by d sigma, so let's write down d squared by ds squared of dv by d sigma. Don't forget I need to squeeze in the half sigma squared s squared, don't I? But, so, shall we? I'll differentiate that in a moment. Plus, so if we differentiate a half sigma squared s squared, what do we get? We get sigma squared. That's come down, hasn't it? So that becomes sigma s squared over 2, agreed? Times gamma. Right? So in other words, this is over 2. No, sorry, the 2's already cancelled out. Thank you. Yes, 2's already cancelled out. There we go. So sigma squared gamma plus, we've got rs times d by ds of dv by d sigma minus r dv by d sigma equals 0. So what this allows us to now do is to obtain a Black-Scholes equation not for the option price but for the Vega term. And I'm going to write down this little v as dv by d sigma. So this then becomes d Vega dt plus d squared Vega ds squared. I'm going to take the other term on the other side. Did we forget a half sigma squared, s squared? That times the derivative of that plus that times the derivative of that. So we need a half sigma squared s squared here, don't we? Agreed? A half, we forgot about that in the excitement. So a half, I think we should make some space here. A half sigma squared s squared d squared Vega ds squared plus rs d Vega by ds minus r Vega is equal to minus sigma s squared gamma. There's the resulting partial differential equation for the Vega term. Rather than solving the Black-Scholes equation first and then trying to obtain Vega from that. Now, in terms of just summing up, we essentially started from scratch in the sense that using ideas that we'd already developed in modules 1 and maybe slightly 2, drive the Black-Scholes equation and solve it. Now, the nice thing is that after this session, we're not going to be solving any more PDEs. This is the only case, because the structure of the Black-Scholes equation here allows it, because it's simple enough. After today, there won't be any solutions. We will either have to resort to numerical solutions, or we'll look for simpler solutions of a particular type. Right? But over here, because of the structure of the Black-Scholes equation and the fact that we could cancel out the s's with the s's, cancel out the s's and the s squareds, we've managed to get a one-dimensional heat equation. This situation will not really arise again. Right? So you will get the full solutions for how to do this, because what we've done here is a detailed outline, but you'll get the full step-by-step working right from the very first substitution through to the final solution of the Black-Scholes equation. And these were essentially the Nobel Prize winning formulas that Black-Scholes and Merton came up with. So I am with you next on Thursday, next Thursday, on the 29th, and there we will look at two popular numerical techniques for pricing derivatives. One is the Monte Carlo method, and the other one is finite difference methods. Right, so the maths will pick up again there, but you will see that the Monte Carlo compared to finite difference method is very, very nice. Okay, thank you. I'll see you then.